One difficult concept that our group struggled with were Kepler's laws of planetary motion. It's easy to be confused because traveling in space is not like traveling on Earth. Let's begin with a real-world example that occurred during the Apollo 13 mission to the Moon.
They are here. We turn them around, straight back, yes. Direct abort.
No, sir, we get them on a free return trajectory. It's the option with the fewest question marks for safety.
I agree with Jerry. Use the moon's gravity, slingshot them around.
So why is Jerry right? Not just because he's the only one wearing a suit jacket, because the destination is moving. Here's an analogy. Let's say the two airplanes leave the airport at the same time and speed. One is traveling 90 degrees east and one is traveling 90 degrees west. The plane traveling west will reach its destination before the plane traveling east because the western destination is actually moving towards the plane due to the Earth's rotation. The destination to the east is similarly moving away, creating a greater distance. This diagram shows Kepler's second law. The area of each shaded section are actually the same, regardless of the shape. The same can be said for volume of water. Here are two glasses of water. Which glass has more water? The tall, skinny glass has 1 cup of water. Even though the short, fat glass looks like it has less, it actually has the exact same volume as the tall, skinny glass, 1 cup. The first law of Kepler's motion states that the orbit of every planet is an ellipse with the Sun at the two foci. The second law states that a line joining a planet and the Sun sweeps out equal areas during equal intervals of time. The final law states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. This is important in the gravitational slingshot in the Apollo 13 mission because Kepler's second law allowed the astronauts to identify the moon's pattern in order to ensure an accurate launch. These concepts impact the course because it allows for precise and accurate predictions of the location of the planets, moons, and artificial satellites. This allowed NASA scientists to use the moon as a landmark and added boost in velocity, thus conserving energy.
So to explain Kepler's laws to non-science majors, I think it's important to break down the topics. So for the law of orbits, it'd be important to understand what an orbit is and what causes an orbit, and maybe even explain gravity. And then for the second topic, the law of areas, it would be important to explain the math of an ellipse and understand that at every point on an ellipse, the distance from both the foci add up to the same distance all around. And then with the last one, it would be important to break down the math. And when teaching these topics, I think the most helpful thing when teaching non-science majors is to have a simulation up on the screen or a diagram. That way, the students can actually visually see the math, how it works out. Visually see that at every point on the ellipse, the area is the same, and that for every planet, the orbit is an ellipse. So for the third law, the law of periods, I think the most helpful thing to non-science majors is actually breaking down the math of the law and explaining, okay, this is a period, and squaring that would be proportional to what the cubed semi-major axis, and explaining what a semi-major axis is. And I think that would be the simplest way to teach it to non-science majors, because these topics do tend to get really hard to grasp, and having, the topics broken down, it'd be easier for someone to understand.